Welcome to the second step of hypothesis testing. So for this video, we're going to focus on finding the critical values. Now, I have a separate video for this compared to the one that you went through for finding critical values for confidence intervals because it requires more thought. And here is why. Now, determining the critical values first requires that you think about this symbol in your H1, your alternative hypothesis. H1 symbol is the only one that matters. If you have a two-tailed test, which is a not equal sign in your alternative hypothesis, and then finding the critical values is identical to the way that we did it when we were finding critical values for a confidence interval. Notice that I have 1 minus alpha, the confidence level in the middle, and then I split my alpha in half for both tails. And that's because it's a two-tailed test. And so that region, or the regions I've shaded in blue, are called the rejection regions. And with a two-tailed test, you could reject if what you observe is very, very small, far on the left, or very, very big, far on the right. And so that's why we cut it in half. But here is where it differs. If you are doing a one-tailed test, meaning that your H1 has either a less than or a greater than sign, so it's not two-tailed, it's one of these two scenarios, then there's no reason to split your alpha in half. You put all of it just on one side, and the side that you're putting it on depends on the direction of your H1. And so when you have a less than sign with the arrow pointing to the left, then you shade in the left area of size alpha or area alpha. And if it's a greater than sign, like the one in the bottom, then your rejection region is going to be on the right-hand side. We do not cut alpha in half. And so it requires that little bit of thought. When you are going to the appropriate table, Z or T, depending on if it's a Z or a T test, you're going to want to make sure you know, are you looking for alpha or are you looking for alpha over 2? That's a really important detail. All right, so let's practice this. And you could ignore that 0.4 and these 0.01s. Let's take a look at the first one here. We want to find the critical value for a 98% confidence interval where sigma is known. And so what I'm looking at here is, okay, we're doing a confidence interval. So that's equivalent to a two-tailed test. Sigma is known, tells me we want to use Z. And so in this case, we're going to put 98% or 0.98 in the middle. That means 2% is not in the center, or half that, 1%, 0.01 is in each tail. And going to the Z table, looking up 0.01. Looking for 0.01 as a probability. I see that it is closest to 0.0099, which corresponds to negative 2.33. But because this is two-tailed or a confidence interval, that's going to be plus or minus 2.33. Which is what I got. What about for the next one? So here we've got a sample size of 17. Alpha is 0.02 or 2%. We're told that it's a two-tailed test, which means we have a not equal to sign in our H1. So we do want to split alpha in half. And sigma is unknown, which means we're going to be using the T table. And so alpha over 2 is going to be 0.01. Degrees of freedom is 16 and minus 1. So we're looking in the 16 degrees of freedom row, the 0.01 column in the T table. So 16 degrees of freedom, 0.01 column. And that brings us to 2.583. It's two-tailed, so that's plus or minus 2.583. And there you have it. And notice I'm labeling also whether it's a T star or a Z star. Let's go to number 3 here. Alpha is 0.04. We're doing a left-tailed test, which means each one has a less than sign in it. And sigma is unknown. Or sorry, I looked at the wrong one. Left-tailed test, but sigma is known. So we're going to be using the Z table. And because it's one-tailed or a left-tailed test, you don't split alpha. So we're using 0.04, not 0.02. So 0.04, we're looking for 0.04 in the Z table. 0.04, 0.04. I see a 0.0401 there, and that corresponds to negative 1.75. And then I think, okay, well, is this a left-tailed or a right-tailed test? And so just reviewing again, it says that it's left-tailed. So we do want to keep the negative sign. And this is Z star equals negative 1.75. Let's jump to 6. Here we have alpha is 0.02. It's still a left-tailed test. And sigma is known. So we're going to be using the Z table. We're going to look up 0.02. And we're going to keep it negative. And 0.02 is closest to this one. You might interpolate because it's almost in between, but I'd be looking for something like negative 2.05, maybe negative 2.055. Either of those would be fine. And there you have it. So in this one, I chose to interpolate, but going with the closer one would be fine. For 8, here we have a sample size of 8, alpha is 0.01. We're doing a right-tailed test where sigma is unknown, which means we want to use the T table with 7 degrees of freedom, and we are not cutting alpha in half. So we're looking under the 0.01 column, 7 degrees of freedom row. Here is 7 degrees of freedom, and 0.01 is there. So I'm seeing 2.998, not the negative side, only the positive side. Positive 2.998. And again, it's positive, not just because that's the value that we got on the table, but because this is a right-tailed test. So I know that the rejection region is going to be on the right-hand side. Let's look at a few more together. I'm going to the next page, and we'll do 10, 11, 12, 15, and 16. And then you'll pause in order to attempt the remaining ones on your own. Of course, we start the video to check yourself thereafter, but that's how we're going to progress. So for 10, here we've got alpha is 0.05. It's a left-tailed test. Sigma is known. Alpha is 0.05, left-tailed. Sigma is known. So Z table, we want a negative value here. And we're looking for 0.05. 0.05 is perfectly between these two, and that's going to give us negative 1.645 when you interpolate. We've seen that one before. There you go. For 11, alpha is 0.1. This is a right-tailed test, so we want a positive value, and sigma is known. So we're looking for 0.1 and using the Z table because sigma is known. 0.1. Make sure you don't add more zeros into this. And 0.1 is closest to 0.1003, which has negative 1.28 as the z-score, negative 1.28, negative 1.28. But this is a right-tailed test, which means I want the positive side only. And so I write positive 1.28. And so you can see that there's some thought going on here. Don't just take the value that you literally find in the table. Think about whether you want the positive side, the negative side, or both. For 12, we're doing a 99% confidence interval for the mean where sigma is unknown, n is 16. And so that tells you that your degrees of freedom is 15, and you're going to be using alpha over 2, which is cutting 0.01 in half. So that's going to be 0.005. So we're looking in the 0.005 column, 15 degrees of freedom row. So 15 degrees of freedom. And I said 0.005. It's going to be that value, 2.947 plus or minus. There you go. We've got two more together. And here we want 15 says n is 12, alpha is 0.05. We're doing a two-tailed test where sigma is unknown. So that means we want to use the t-table with 11 degrees of freedom. And you're going to cut the 0.05 in half. So we're looking at 0.025 because it's two-tailed. So 0.025 column, 11 row. 0.025 column and 11 rows. So this is 11 row. 0.025 is this column. And I am seeing 2.201. 2.201. And this is two-tailed, so we are going to make that plus or minus. And then finally 16, alpha is 0.65. This is a right-tailed test where sigma is known. So we're using the z-table. And we want to try to find 0.65. But if you look, you'll see that the largest value is 0.5. So it doesn't go up to 0.65. But we could do a quick sketch just to visualize this. If we want a region with 0.65 shaded, and it's a left-tailed test, so that's on the left side, then I know that the area is going to be, or the line is going to be to the right of 0, because 0 is in the middle, so that's 50%. So 0.65 has to look something like this, which means that our critical value is actually going to be on the positive side here. This is an unusual case. You typically wouldn't have alpha this big, but it does test your understanding of visualization and reasoning. So we can't find 0.65 in the table, but the complement, 0.35, we can. And if we look for 0.35, or the closest value to it, you should find that it is almost perfectly between these two values here in the bottom right. So that's negative 0.38 and negative 0.39. And so maybe negative 0.385, possibly just negative 0.38 because it's a little closer to that one. But since this must be on the right side, I'm thinking around positive 0.385. So let's go ahead and see if that's what I had gotten. And it does look like it is. I didn't interpolate here, but I went for, oh, sorry, this is a right tail test. Right tail test. So The picture is a little different. It's actually a mirror image. Let me fix that for you. So that means that our shaded region for a right tail test is going to look something like this, where the area of that region is 0.65. And so the area to the left here is 0.35, which is why this should be negative. And somewhere around negative 0.38, 39, 385, but somewhere around there. Yeah, it's 0.002 or 0.0017 away. So it's a little closer to the 0.3483 value. All right, like I mentioned earlier, at this point, pause the video, go back to the problems that we haven't done together, attempt to find the critical values on your own, label them, make sure you think about whether they're positive, negative, or both, plus or minus. And then when you're ready, start the video back up to check your answers. So let's see how you did. I am just going to one by one show the answers for each. For number 4, where sigma is unknown, you should have used the t-table, and hopefully you got plus or minus 1.761 because this was for a confidence interval, so you should have both sides. For when sigma is known for the next one, problem 5, you're going to be using the z-table, and you should have plus or minus 2.575. That's for a 99% confidence interval, one of the well-known ones that we found before. For number 7, where sigma is unknown, this is going to be using the t-table again. And this is another confidence interval scenario, so you should have plus or minus. Moving to the next page. Number 9, it's another confidence interval one when sigma is known. I'm sure this is a well-known value by now for you. That's plus or minus 1.96 from the z-table. Then 13 and 14. 13 sigma is known, 14 sigma is unknown. So the top one is the z star value, the bottom one is t star. You have a confidence interval of 13, so that's why plus or minus, and a left-tailed test with a small alpha for 14, which is why it's only negative, not the positive side. And then lastly, for 17, which is another confidence interval when sigma is unknown, you should have used the t-table and hopefully obtained plus or minus 2.821. Hopefully this help made you feel a bit stronger about finding critical values when you're doing hypothesis testing. The next step is going to be putting all of this together in order to actually thoroughly, from beginning to end, conduct a hypothesis test.